So if you've been following the news and you can't help but hear just a little bit, if you're a news junkie, about the Rosetta spacecraft that's been orbiting that, I can't pronounce the name of the comet, but this comet is ever getting closer to the sun, so it's vaporizing a little bit. But anyway, Rosetta sent a probe. So Rosetta's still orbiting the comet, but the probe tried to land on the comet. I say tried, and it did. Actually, the news thing that we watched, all the scientists were happy and everything, but honestly, it basically, this is what I had heard described to me, it basically landed on the comet, okay? It didn't have the anchors like it wanted to, and we kind of knew that, okay? And basically, it went up in the air, okay, but still gravitationally attracted to the comet, okay? And 2 hours later, again, 2 hours later, it landed back on the comet, okay? And then did one more little bounce, okay? It's like, whoa. So it's on the comet, and they're trying to get some data. It's not where they wanted it to be, which means that kind of they don't have all the sunlight they wanted to, and that's important because that was what's supposed to energize the cute little probe. So still exciting, okay? And at the news conference, before they knew all this kind of all that stuff that was going on with the probe, one of the scientists that first spoke said, the problem with this is it looks easy. And I thought, well, how true? We're all kind of sitting back, and we see this stuff every day. Not. And he went on to say that it was only through, and it probably involved some math, but only through hard work and ingenuity, and did they take the 10-year trek to get to the comet and do what they're doing. So anyway, all right. So the last chapter we talked about the Milky Way galaxy, and now we're going to talk about galaxies in general. So we got some pretty pictures. One of the reasons I think we're going to be able to get through 90 slides without much trouble is because there's a lot of pictures. So here, actually, I don't know if you can make out that this is the Big Dipper, this is the bowl part of the Big Dipper, these 4 stars, and here's the handle in the Big Dipper. And the Hubble Space Telescope, one of the awesome pieces of equipment that's orbiting the Earth, one of the first things it did, actually, the Hubble Space Telescope, was to pick a spot, and it picked this spot, kind of cool because we love the Big Dipper, and where there was nothing, and it honed in on it. So if you take this little box and magnify it, now you can start to see some stars. If you take that little box and magnify it some more, those aren't stars, those are galaxies in general. You're like, oh, how lovely, okay? That's just amazing, beautiful. So we're going to talk about galaxies in general. And I think today we'll get to it, but it wasn't until 1923 or so, after 1923, that we understood the idea that there are galaxies of stars out there. The concept of a galaxy was like, I don't know. They didn't know whether actually these were like, these fuzzy things were like nebula, like a dust, okay, or whether they're galaxies. So, the term cosmology, and we'll be talking more about cosmology in Unit 5, but when I think of cosmology, I think of not only just galaxies, but kind of how our universe is arranged. Okay? The last phrase on the video we watched on Wednesday said something about a speck on a speck on a speck on a speck. That's us. Okay? We're on the Earth that orbits the sun, which is a star, and hundreds of billions of stars in our galaxy. There are hundreds of billions of galaxies in our universe. So, cosmology. So, on the test, if I ask you the 3 major types of galaxies, because I will, okay, I'm going to tell you what to put. So, again, here's kind of that deep field image taken by the Hubble Space Telescope. Now, the Hubble Space Telescope has an assortment of cameras on it. So one type of galaxy is a spiral galaxy. Okay. Another type of galaxy is an elliptical galaxy. And I have some more slides coming up. Now, this isn't a type of galaxy, that one of the 3 types of galaxies I need you to know, but an irregular galaxy is kind of a catch-all. Okay, spiral, elliptical, and the other one's coming up. Irregular galaxies. They're irregular because maybe they're transitioning between another type of galaxy. They could be irregular because something smashed into them, like another galaxy. They could be irregularly shaped because they are like the baby galaxies, the very beginning of the universe. So this might look familiar. Okay, this actually looks like it could be the anatomy of the Milky Way galaxy. Okay, we talked about the bulge in the Milky Way galaxy. We talked about the spiral arms of the Milky Way galaxy, the disk portion, the halo portion. In the halo portion, there are globular clusters. Okay, so it's almost like a little review slide. Now, one of the things we're going to see, not till the very end of chapter 16, but actually most galaxies, whether they're a spiral galaxy like this or a barred spiral, I'm going to show you here in a minute, they harbor, I like the word harbor, like they're being sneaky, a black hole in the middle of them. And we've talked about black holes before. If a massive star ends its life, it could leave a black hole. But these types of black holes are called supermassive. So if any time you hear the term supermassive black hole, that's the one in the center of a galaxy. Sagittarius A star, supermassive black hole in the center of the Milky Way. So this is the sombrero. Doesn't it look like a sombrero? This is the sombrero galaxy. One of the things that, sombrero galaxy. It's another spiral galaxy. We can't see the spiral arms because it's more kind of like tilted. We can just kind of see the disk. But like the Milky Way galaxy, it's awesome because we can actually apply what we know about the Milky Way and apply it to other galaxies. We said the disk stars in the Milky Way were kind of young stars. Okay, we said that the halo region of the Milky Way galaxy, they were kind of older stars, metal poor stars in the halo. Okay. So remember, anytime you see the term spheroidal, okay, actually that just means the halo region of a galaxy. So this now is not looking at the edge on, this is looking more at a face-on picture of a galaxy. Just beautiful. So the third type of galaxy, so spiral galaxies, elliptical galaxies, and this would be the third type of a galaxy, the barred spiral. And actually, as it turns out, our Milky Way galaxy, I think they used to think that our Milky Way galaxy was a spiral, and it is a spiral, but more specifically, it has a bar of stars that kind of extend from its center, okay? So this is a barred spiral galaxy, and we think that actually the Milky Way is a barred spiral galaxy. That's not a picture of the Milky Way, but... So irregular galaxies are kind of miscellaneous. Another type of miscellaneous galaxy is lenticular galaxies. And like the slide says, galaxies we think could kind of evolve, okay, between different types of galaxies. And this might be kind of a middleman between spirals and elliptical galaxies. Okay, so you know what a spiral galaxy is. An elliptical galaxy is just kind of more, it's just kind of more like a ball of stars. It's a galaxy. So here's a picture of an elliptical galaxy. Actually, galaxies are kind of organized in clusters. And actually, clear back in Unit 1, we talked about the organization of the universe. So galaxies are kind of in families called clusters. This is a cluster of various elliptical galaxies. Elliptical galaxy. Okay, I'm kind of thinking the fuzzy sort of things at this distance are galaxies. And the fact that you don't see kind of a disk, okay, those are elliptical galaxies. Just a blob of stars. So I'm pretty sure, I didn't look this up, but this sure looks like pictures I've seen of the Large Magellanic Cloud. Okay, Large Magellanic, I think, cloud, affectionately called the LMC. And actually, it's an irregular galaxy of stars. Looks kind of beat up, doesn't it? The reason that I've never seen this, I've only seen pictures, is actually it's a southern hemisphere object. A lot of those out there. Drat that southern hemisphere. So if you're familiar with a tuning fork, Like if you're a musician, to get to pitch, what they used to do instead of having their smartphones to go, you can get pitches on your smartphone, is basically take something that has prongs, hit it against something and go, it would vibrate at a certain pitch, and you could tune your instrument. So that's a tuning fork. So I mentioned that because Edwin Hubble, which we're going to see kind of the neat things that Edwin Hubble did. We're going to see a picture of him in a minute. But he used something called the tuning fork diagram, where this is the handle of the tuning fork. And he links those 3 types of galaxies I told you to know. So E stands for elliptical galaxies. S stands for spiral galaxies. Now notice there's an S sub A, S sub B, S sub C, but they're all spiral galaxies. And SB stands for barred spiral galaxies. So these are the 3. I'm sticking with Edwin Hubble. So when I ask for 3 types of galaxies, this is what I'm after. Okay. So if we kind of compare elliptical galaxies with spirals and barred spirals, we could make a general statement with regard to the disk component, okay, and kind of the spheroidal component, which is kind of what we say is the halo region in a spiral galaxy. So here, there's kind of no disk. So the spheroidal component dominates. There is a disk, whether it's a spiral or a barred spiral. And so the disk dominates. Another thing, actually it's on the term for this chapter that you'll need to know, is the relationship between the size of the nuclear bulge and the wrapping around of the spiral arms. And it's kind of summarized in that arrow. So what that arrow in the middle of the spirals and the barred spirals says is that, and I kind of look at it this way, I say the tighter the spiral arms, okay, the larger the bulge. Okay, that's kind of how I think of it in that step. Because what we found, or what scientists have found in studying other galaxies, well, first off, are we okay with, when it comes to, if the center of me is the bulge, and these are the arms, obviously, okay, does it work for you that the bulge actually kind of puffs out a little bit from the disc, or can be kind of flat with the disc, okay? We kind of have this bulge thing kind of doing different things. So the spiral arms can do different things too. So what they've seen is the more tightly wound the spiral arms, basically the thicker the bulge, and the looser the spiral arms, the thinner the bulge. That's all it means. But I had to pick something to put on your test. So I mentioned a little bit ago that we saw kind of a big old elliptical galaxy, no disk, mostly just stars. And it had a bunch of other elliptical galaxies around it. So galaxies are grouped in what we call clusters, okay? And actually, and I guess we won't talk about this until the next chapter, the Milky Way galaxy is a member of the local group cluster, okay? So this is another cluster of galaxies. But these look like kind of an assortment of spiral galaxies. Now, I didn't chase it down, and in your textbook it probably says, but I'm betting this is a photograph instead of an artist's rendition. That's so pretty. Okay, so what you're seeing there is another group or another cluster of galaxies. On the previous slide, it was a cluster of galaxies that looked like it had some elbow room between the galaxies. Not so much here, right? Okay, so sometimes galaxies of stars can be kind of densely packed together. And when it comes to looking at clusters that are densely packed like this, or clusters that are kind of have some elbow room, like you saw on the slide before, scientists see that elliptical galaxies sometimes have these like, kind of are tightly, these groups of, these clusters of galaxies are kind of packed more than the other. Okay, so one of the things that, in order to kind of put a perspective on our universe, that we really need to be able to do is, from our point, know how far away a galaxy is. Okay, so we're going to actually, I'm going to build up to that point. And there are, I think, 6 steps. I don't know if we'll get to all of them today. But just measuring the distance between us and something cool in the sky. And what this says is, what this little animation will show you, it's not really an animation, but is what appears to be very similar, maybe with regard to distance and brightness, is not always necessarily so. So we have two objects that they look to be the same brightness, okay? But as you know, brightness depends upon two things. And when we say brightness, we mean like apparent, what it appears to be. Brightness depends on how much energy that thing's pumping out and the distance between us and that object, because we know that light will be diluted over distance. Okay, so, dun-dun-dun, revealing these objects that appear to be the same brightness. Actually, one is a candle and another is a lighthouse. So one of the things we're going to talk about in the next few slides is what scientists do is they make use of the fact, for instance, of this phenomenon. So we would say actually this has high luminosity. I like the red on black. I think that's fun. High luminosity. What does that mean? It means the energy is pumping out per second, okay? But it actually is at a further distance compared to the candle. And it's that distance that gives it time to dilute the light. So that's why they appear to be the same. Oh, yeah. So we can make use of that. So hold that thought. So there are, like I said, I think 6, maybe 7 steps. And each step is actually literally kind of a step going farther from us for us to be able to kind of gauge distance. So the first step is simply something called radar. And to kind of show you what we mean by radar, and it's the closest of the steps, okay? There, your author has this cute little applet. Okay, we use radar all the time in weather. Okay, we actually, for instance, to track clouds, okay, we basically send out a signal and we look for the signal to come back. If the signal doesn't come back, there's no clouds or no precipitation. If the signal comes back, it's hit a cloud or precipitation. We call that reflectivity. So that's radar. So we can actually then, like this, you can imagine, the longer it takes that signal to come back means it's farther distance to the bottom. This actually, if you're a fisherman, it's been a few years since I looked into it, but it seems like cheating if you're trying to find, you could do this to find fish, right? So, anyway. So, kind of related to that then, we actually can use radar to close cool objects, and those close cool objects would be planets. Okay, so not drawn to scale, right? Because you see that humongous, that's the Earth, obviously, the pretty blue marble. And there's like a humongous satellite on it. So the way this applet works is I could go ahead and I could point it at an object. So I guess there I'm pointing it at Venus. Okay. And notice that in that configuration, Venus is really close. Okay, and so it doesn't take very long for it to come back. It takes a signal round trip, 7.2 minutes. Okay, and that's the distance. If we compare that to, I'll set my sights on Mars. Okay, Mars is farther away. I could send a radar signal out and look for the reflectivity. Notice instead of 7 minutes or whatever, it's like 40 minutes. Okay, and there's the corresponding distance. So radar works. Okay, for close objects. That's step 1. Step 2, déjà vu. Okay, we said actually it's an exciting thing. We said that even though we see these cool constellations like the Big Dipper, actually the Big Dipper is a subset of Ursa Major, but we see these cool constellations. We're like, yeah, you know, that's a set of stars that are fixed together. But if a star is kind of close to us, actually, as we orbit, as we change our position, orbiting the sun, we will see that star in different positions against the background stars. And so that's called using parallax, or that's called the effect of parallax. And so here actually, remember how this works is this is the star of interest, relatively close. These are the background stars. In January, okay, we see that star here. And in July, we see that star over here. Hope you're not counting on that star being part of your favorite constellation, okay, because it will actually move against the background stars. So if a star is close enough to us, we see parallax. And I don't know if you remember kind of the whole math thing, but depending upon this wiggle, we can actually get to distance. So that's further than radar, using parallax. So now building up to step 3. That was step 2. And actually, I think steps 3, 4, and 5 use this technique, which is very similar to the whole lighthouse and candle. Okay? So the whole lighthouse thing, we said that the light is diluted as you get farther from the lighthouse. And this is just showing you that, I really like this figure. And again, it's another deja vu figure. It's basically saying we have a certain amount of light here that is diluted up to from 1 square to 4 squares, and from 4 squares to actually 9 squares there as you get farther from the source. The dilution of light. It's diluted by what we call the distance squared. So, you remember this? You put it on your note cards. Okay. We said the brightness that we see in objects, so that's what we're seeing it as, that's brightness, is equal to how much energy it's pumping out divided by 4 pi times its distance squared. Well, if we're after distance, okay, we can rearrange, what we call rearrange in math. We can rearrange and solve for distance. So what this says is if you have an observable brightness, okay, and if you know how much energy that object is pumping out, okay, which we do for some things, you can do the luminosity divided by the brightness, actually the square root of the brightness, and get to distance. But in order to know the luminosity of an object, we use, in general, it's not really a technique, but we use the fact that certain objects, we know their luminosity. Those certain objects are called standard candles. Okay, so a standard candle. And I kind of liken it to when you go to your cupboard, I don't know where you store your light bulbs at home, but when you go to your cupboard, sometimes you have options. So you're like, well, I think I want a 60-watt bulb. Or, oh, I want really bright. I'm going to take a 100-watt bulb. So your package is telling you, oh, the luminosity that thing's going to send out, okay? So that's what we count on. And so certain objects, and I'm going to talk about certain objects that scientists can hang their hat on what the luminosity is, and those are called standard candles. And then all we got to do is compare it to the brightness, and bada boom, we have distance. Okay, so using standard candles is this first standard candle I'm going to talk about. This first standard candle is something we talked about before, main sequence stars. Now these are this is sort of like an HR diagram. I'll show you what's different about it. First, what's similar about it, remember the Hertzsprung-Russell diagrams, and actually that awesome diagonal line, these are actually, I'll just put MS, these are actually main sequence stars. Okay, that kind of, we said actually these are brighter at the top, and these are dimmer, which is cool because they are less massive and all that. What's different about this HR diagram is instead of absolute brightness, actually we are putting apparent, or absolute luminosity, sorry, instead of luminosity, we are putting apparent brightness. So what this is saying is we have 2 clusters of stars. The Hyades are in Taurus the Bull, and actually the Pleiades are also in that same constellation. They're beautiful, and I have a picture of the Pleiades coming up. The Pleiades are sometimes called the Seven Sisters. Okay. So these are 2 clusters of stars. Okay. But if I were to ask you which one's brighter, you probably would say the Hyades. Don't they look like they're kind of on the brighter end? Okay. So again, this is kind of a modified HR diagram. They appear brighter, okay, than the Pleiades, collectively anyway. Since they appear brighter, okay, they must be closer. And that is the truth. Okay? And so we use the fact that we know a lot about how bright main sequence stars should be. Okay, so that actually is step 3. Brighter means closer. So, did you guys need that? Okay, good. So this, we'll pause just a minute. This is an open cluster. Okay, there's globular clusters and open clusters. So this is a set of stars, so we're all born about the same time. So this is the Pleiades we saw on the kind of modified HR diagram a minute ago. And this is sometimes called the Seven Sisters. And there is a cool story, I would say Indian story, about these 7 maidens that were rescued. There's a lot of rescuing going on in mythology and constellations in the stars. So they're the Pleiades. They are known as M45, Messier object number 45. And sometimes, okay, they are called, and I guess not officially, but unofficially, they are called the Little Dipper. Little, and the reason I have 2 littles is it's not the real Little Dipper. And the reason people say that, when students first told me that, I'm like, what are you talking about? And then I'm like, oh, that's what you're talking about. Okay. I'll put one more thing up here, or another thing up here. If you have a pair of binoculars, they are amazing. Binoculars. They are totally, this open cluster is amazing through binoculars. It's the constellation Taurus, so it's coming up earlier and earlier. But let me put it in perspective of the Little Dipper. Okay, so the Pleiades is about, oh gosh, I don't know, maybe the size of one of my fingers. Okay, if you extend your arm. Okay, the Little Dipper is probably maybe 1.5 times the size of my palm. Okay, so if this is like 8 or 10 degrees, that's like 12 degrees for the Little Dipper, and maybe 1 degree for the Pleiades. So they're totally different, but they're kind of similar. This is where, especially if I'm at the observatory helping, I'm kind of like, oh, that's okay. You can call that the Little Dipper, because it kind of looks like the Little Dipper. Okay. So, that was 3, step 3. If you want to put step 4 here, you can. My steps actually are kind of after I build up to it. So that was using main sequence stars as a standard candle. We know how luminous main sequence stars should be. Another standard candle are the Cepheid variables. Now, remember we talked about main sequence stars, and you can kind of see, this is a true HR diagram. This might kind of, okay, so that was a faux HR diagram before. Those are main sequence stars, and we said that these are giants, okay? And actually, as we kind of talked about, as the star leaves the main sequence, sometimes they kind of wiggle up there in the giant region. And Cepheid variables actually pulse, and sometimes, I don't know, as much as like 30 days or 10 days or 100 days. But they actually get brighter, okay, that's a Cepheid variable. Okay, just a star up there, and we'll call the instability strip. Okay, but the cool thing is, and the reason we can use it as a standard candle is, and I'm going to show you here in a minute, we can use its pulsing. Okay, by the way, here you're seeing one Cepheid variable and doing its pulsing thing. Here it's where it's bright, and here it's where it's dim. Bright, dim, bright, dim. Okay. Now, one thing I haven't said yet is that this is amazing. Okay. We're going to see that Edwin Hubble actually looked at a Cepheid variable. He studied. You can't just look at it because you have to study it over time. He studied a Cepheid variable star in the Andromeda Galaxy. Is that not amazing or what? Okay. So in this case, you have to be really patient to be in anything, and a lot of things with regard to science, including astronomy. So 50-day period. All right, so here's the deal. Here's how we can use them as a standard candle. Oops, let me go back. So each of these dots is a different Cepheid variable, and what you have along the x-axis is how long it takes for them to do one of these. Okay, so 3 days, 10 days, 30 days. It doesn't look like a logarithmic scale down here, does it? 100 days. And then what you have along the y-axis is your standard candle information. So the standard candle information says this. If it, for instance, if you have a cycle of getting brighter and getting dim of 30 days, okay, we know that the luminosity of that Cepheid variable is a little over 10,000. And what that means along the y-axis is if you go to your cabinet and grab that Cepheid variable, it actually is, with regard to its luminosity, 10,000 times the luminosity of our sun. So you know what its luminosity is. So like you saw in the equation earlier, you take its luminosity and you compare it to its brightness, and you got distance. Okay? So that's how that works. So step 4, using Cepheid variables as a standard candle. I'm not going to play this little animation for you because it looks way too complicated. We'll stick with the graph we saw a minute ago. Okay, so that was step 4-ish. And actually, this is step 5. Okay, this is going to be step 5. Even brighter than a Cepheid variable is a supernova event. And specifically, we talked in the last 2 chapters ago, and this is in the same unit, there's 2 types of supernova. One is with a white dwarf, we call that 1A, okay, and then the other one is a massive star, we call that a type 2 supernova. But if a 1A supernova goes off in a distant galaxy, far, far away, okay, we know its luminosity. We can use it as a standard candle. Okay, and the reason it's step 5 is because we can see those even farther than the Cepheid variables. So this actually kind of comparison, this is a galaxy. It doesn't look like much of a galaxy, does it? It's all pixelated and all that. But this actually is the same galaxy that has had a supernova event occur in it. Okay, so we get the brightness of that, and we compare it to the known luminosity of a supernova, and we got distance. Okay, another pair, and another pair. So these kind of top and bottom are just, pairs of without the supernova and with the supernova. I just think, I don't know, scientists must have astrophysicists must have a sense of humor because, looking for those events. Actually, one of the videos we watched said, remember where, and I think it's Alan Pinko or something. Anyway, he said that he has a telescope that just automatically looks at galaxies and looks for something like this to go off. Okay, it's kind of it went something like looking for a nova event or supernova is kind of like looking for a flash to go off in a crowd of people that are like at a stadium watching a football game. Okay, so I said it just a minute ago. Remember when we looked at Hubble's deep space image of all those galaxies? Just beautiful. And it wasn't until the 1920s or so that we understood that the concept of there were galaxies of stars out there besides the Milky Way galaxy. Okay. This is actually kind of leading into that topic. So, of course, we all know that Andromeda is let's see. Let me kind of stay consistent with my slides. I kind of edited my slides for the last few semesters, but I was thinking about this. If you go back historically again, I think it's the Curtis-Shapley debate. Okay, 2 astrophysicists at the time, 1921, I think maybe. And actually, that debate kind of reminded me a little bit of Pluto debate. Was that 06 that Pluto was demoted-ish? Okay. So what both debates had in common was basically the scientific community got together and talked about something. In the case of Pluto, it was like, how do you define a planet? In the case of this debate, it was like, okay, we see these spiral things up there. Spiral things, nebula things. And they could just be like a nebula, or they could really be a galaxy. And Edwin Hubble, like I told you, used Cepheid variables to ultimately come up with distance. Let's see, where is it? I'll just add the word in case because I'm not finding it here. Edwin Hubble actually used a Cepheid variable in that galaxy, which is a beautiful picture of that galaxy. That's the Andromeda Galaxy. Edwin studied a pulsating Cepheid variable, looked up its luminosity, and then compared its luminosity to its brightness to get distance to this galaxy. So although we all know that this is the Andromeda Galaxy, they used to think, hey, is it a nebula or is it a galaxy? So there, finally, and I don't have as many slides as I probably want to or should, but historically, there's Edwin looking. We don't know what he's looking at, but there's the telescope. There's the whole telescope. So here you see that he used, and actually this is on your test in some form, he used, like I said, Cepheid variable as a standard candle, okay, to get the distance to the Andromeda Galaxy. And from then on, it's like the scientific community's like, oh, yeah. Those things that look kind of fuzzy, you know, and aren't globular clusters and aren't open clusters, because those are part of our Milky Way galaxy. Clusters are part of our galaxy. Those things that look kind of fuzzy, they're in other galaxies. I just think that is so cool. Makes you wonder what else is around the corner. Well, this caption we've seen now for the second time, how many galaxies are there in the universe? And I don't really directly answer that question in my lecture notes. But it's a matter of kind of density, basically. You kind of like, you know, Hubble looked at one area and said, okay, there's this many galaxies, and then you kind of extrapolate that to the rest of the universe. And I think I might have shown you some of my links that there are basically 100 billion other galaxies in the observable universe. And there's about 200 billion stars in our own galaxy. All right, so I think we stopped at step 5. I'm leading up to step 6. And each time we take a step, basically, we're able to gauge the distance further in space. So one of the things that we've talked about early in here is that we said that something called the Doppler effect, we talked about red shift and blue shift. And if something's going away from you, actually its wavelengths will be elongated if it's sending you a signal. We call that the red shift, or a red shift. And I think I mentioned this clear back in chapter 1, or your text does, that Edwin Hubble actually recognized that all galaxies are moving away from us. I know we talked about it because remember the whole raisin cake thing? Yeah. Okay, so all galaxies are moving away from us. Well, if they're moving away from us and sending us light, which they are, actually all sorts of electromagnetic radiation, then we should see a redshift in the information they're sending us. And we do. So this actually is showing you, the top one is what I call the library sample. Okay. This is what a stationary signal should look like. Okay. And then the bottom one is actually showing you the moving galaxy. Not only is it moving, but it has what we call radial movement, I guess, away from us. Okay, so that's quite a shift. Notice that it is shift to longer wavelength, redshift. So kind of honing in on that little peak thing. So this is an adorable little animation. I love a cute little picture of an observatory. So I've said it before that it's getting kind of cold maybe to go out to the Whitty Observatory, but if you don't get out there this semester, I really hope you do go out to the observatory complex sometime. We've got 2 of these. We've got 2 of these cute little houses for telescopes, right? And so this is showing you what Edwin Hubble did, and I can click on these, okay? And so it'll show a little picture of the galaxy, and it'll give you 2 pieces of information about the galaxy. It will say how far the galaxy is away from us, and it will say how fast it's moving away from us. So what Edwin Hubble did is that he made a scatter plot. Okay, so can you see kind of the dots appearing? down here, each one of those dots is a galaxy. And what it's creating is something called Hubble's law. They're a bunch of galaxies. So Hubble's law, you're going to see it here in a minute, is basically along the x-axis, we plot how far away the galaxy is from us. So each one of these red dots is a galaxy. Along the y-axis, we plot, okay, we know that it's moving away from us, but how fast is it moving away from us? So basically, what Hubble found with the scatter plot is that the farther away the galaxy is from us, the faster it's moving away from us. The farther away it is, the faster it's moving away from us. This is just like the raisin cake. It really is. So here is a clean version of Hubble's law. Okay, so those dots are galaxies. And again, along the x-axis is how far that galaxy is away from us. And along the y-axis is how fast it's what we call recessional velocity is. It's funny because I think instructors really need to pause when they get to this point and say, not all galaxies are moving away from us. Because actually, there are galaxies in our local group, like the Milky Way galaxy, that we are on a collision course for the Milky Way galaxy. Now, I watched a video just recently on that this is the Milky Way, this is Andromeda, okay? And the video was really pretty good. And it said that this actually is going to occur in about 4 billion years, which I thought was cool because it kind of coincides with our sun leaving the main sequence. Isn't that fun? And then the video, the video went on to kind of talk about, and galaxies do this. I'll kind of show, you know. But it said that our nighttime sky ultimately would look really kind of cool, but that the sun would not like run into any other stars. So neat. I'll try to link to that. Oh, before I go on, okay. So let's see what my next slide is. Maybe I do want to go on. Okay. So basically, we can use the redshift, like when we get a signal from a galaxy, we can compare it with our library sample. We can see how much it's shifted. The more it's shifted, that means the more redshift, that means it's moving faster. And if it's moving faster, then we can go ahead and know that it's farther away because it's moving faster. If there's not much redshift, okay, that means it's not moving very fast from us. It must be pretty close. Okay, so that actually is step 6, step 5. I've kind of lost track. So in other words, we can get to distance, and I'm not going to make you guys do any calculations or whatever, but we can ultimately get to distance knowing its velocity. And what we do then is all we have to do is to basically in some way or another divide its velocity by what we call h0. And h0 is Hubble's constant. Hubble's constant. And if you're familiar with kind of how lines work, actually Hubble's constant is the slope from Hubble's law. If you don't kind of track the whole kind of straight line thing, don't worry. Okay. Yeah, so I've been leading up to step 6. Step 6 is look for redshift and use Hubble's law to backtrack to distance. That is so cool. So to kind of summarize what we've done so far, I like this summary slide. So step 1 was radar, planets, right? Step 2, nearby stars, parallax. Okay. Then we have some steps where you're using standard candles. So using the standard candle within a cluster of stars, we could use what we know about the luminosity of main sequence stars. Okay. Notice that there's some overlap with these steps in finding distance. The next one, we also use a standard candle, Cepheid variable, can see a little bit farther, actually extending to galaxies. I just think that's amazing. And then the other two are kind of similar ranges. We said we could use nova or supernova events, for example, is a distant standard. Okay, supernova events, we said. And then down here is the redshift. Oops, sorry. Redshift, Hubble's law. i.e. redshift. So that's how far I wanted to get, and we're going to take a running start at this topic on Monday, and we should be just fine for getting through these slides. Okay? So no assignment due Monday, but Monday we'll knock out this chapter and be ready for your test on Wednesday.